Determination of phase margin and gain margin from the bode plot. Once the bode plot is drawn on the graph sheet, then how to find the gain margin and phase margin, which are very important to analyze the system and to find the stability of the system, and of course in design also we use these specifications. Now, so for a typical system, I have the magnitude plot like this. So we have magnitude plot which is shown here, and also I have phase plot like this. As I said, magnitude and phase plot should be plotted on the same semi-log graph sheet. So now this is available to me. Then how to find gain margin and phase margin graphically? So analytical procedure is different and graphical procedure is different, that the concept will be same. So before going to find the gain margin, we will look at what is the phase crossover frequency. As per the definition of the phase crossover frequency, it is the frequency at which the phase angle of g of j omega is equal to minus 180 degrees. Now the phase plot is available here, and the right side we have phase angle axis. I'll look at where is the minus 180 degrees. So here I have minus 180 degrees. So, and this line you just look at, your phase plot is intersect in the minus 180 degrees line. So that particular point, what is the frequency? That frequency is the phase crossover frequency. And we know that using phase crossover frequency, we can find the gain margin of the system. Now, so 180 degrees, we draw horizontal line where it is touching the phase plot. So it is touching the phase plot here. Now, extend this line onto the magnitude plot. So we need to draw the vertical line from where the phase plot is crossing the minus 180 degrees line. That means that omega PC I am going to extending like this. When extend this onto the magnitude plot, that point is called MPC dB. We know what is MPC, it is the magnitude at omega PC. So this point is now MPC dB because the axis is in dB. That point is MPC dB. What is the gain margin? Now it is very simple. The gain margin is dB minus of this MPC dB value. Means if you look at here, and it is going to be already minus. It is below the 0 dB line. So below the 0 dB line, we have MPC dB. Then gain margin is going to be minus of that value. Then the gain margin is going to be positive, which means if MPC dB is below 0 dB line, my gain margin is positive. Next, so now the steps are very clear. At 180 degrees, you draw horizontal line onto the phase plot. That point is omega PC. Extend the line, vertical line onto the gain margin. Magnitude plot, that is MPC dB. Gain margin in dB is minus of MPC dB. So this way we can find out the gain margin. Now look at the phase margin. To find the phase margin, first locate what is the gain crossover frequency. So the gain crossover frequency is the frequency at which the magnitude of g of j omega is unity, or the magnitude in dB is equal to 0 dB. So absolute value m is magnitude is 1. When it converts to dB, it is 20 log 1 is 0. So 0 dB line is my reference axis. In the phase minus 180 degrees line is a reference axis. Now 0 dB line, look at 0 dB line where the magnitude plot is crossing. If the magnitude plot is not crossing, we can try to extend the line onto the 0 dB line if it is possible. If it is not possible, we can say there is no omega GC at all. Now in this particular plot, I have 0 dB line and it is crossing at this particular point, that is omega GC. So once omega GC is available, you just extend a vertical line onto the phase plot. So once it is on the phase plot, that point is called phi GC. So phi GC is the phase angle of j of j omega at gain crossover frequency. What is the phase margin? 180 plus phi GC. So if you look at here, what is the difference between from phi GC to 180 degrees? So this is nothing but my phase margin. So directly we can look at from that phi GC to 180 degrees. So if phi GC is above 180 degrees, then phase margin is positive. If phi GC is below 180 degrees, the phase margin is negative. Similarly, magnitude plot. So if MDB MDB PC is or MPC dB point is below 0 dB line, then gain margin is positive. When this is above 0 dB line, the gain margin is going to be negative. So when gain margin is positive, then phase margin will also positive. If gain margin is negative, phase margin is also negative, because we know that the bode plot generally plot for minimum phase open loop transfer function. When we plot this on minimum phase open loop transfer function, then either you get both positive or both negative. If you are unable to calculate, we can look at the other one to find the stability. So what is the stability condition? For stability, my gain margin should be positive and phase margin should be positive. And omega GC, because omega GC is the at which your frequency at which magnitude plot crossing 0 dB line, must be less than omega PC. Omega PC is the where phase plot is crossing minus 180 degrees line. So when omega GC is less than omega PC, then the system we can call it as stable system. So if it is a reverse, which means if the gain margin is negative, phase margin is negative, then my system is unstable. In that case, your gain crossover frequency is greater than the phase crossover frequency. So we know the stable, we know unstable. Then the other one is marginally stable. So what do you mean by marginally stable? If gain margin is 0, that means, and phase margin is 180, phase phi GC is 180, which means phase margin is 0, gain margin is 0 and phase margin is 0, then we call the system is marginally stable system. In that case, your omega GC and omega PC both are same. For any system, if omega GC, omega PC are same and the gain margin is 0, phase margin is 0, then we say the system is marginally stable system or critically stable system. Our system gives continuous oscillations. We can also call it as oscillatory system, which is very important in control systems.